Thank you for joining us tonight. My name is Jude, and on behalf of Harvard Bookstore, the Harvard University Division of Science, and the Harvard Library, I am thrilled to welcome you to tonight's event with John Edward Huth, discussing his book, A Sense of Space, A Local's Guide to a Flat Earth, the Edge of the Cosmos, and Other Curious Places, in conversation with Jacob Barandes. Please take a moment to silence your cell phones and other electronic devices. This event will conclude with some time for your questions. Just raise your hand and our speakers will call on you. I will come around with a microphone. If you have not picked one up already, you can purchase a copy of A Sense of Space at the table outside of the lecture hall. After the event, John will be signing copies of A Sense of Space inside of the lecture hall. Lastly, thank you for buying books from Harvard Bookstore. Your purchases support our award-winning author series and helps ensure the future of a landmark independent bookstore. Now, I am pleased to introduce tonight's speakers. John Edward Huth is the Donner Professor of Science at Harvard University. He has done research in experimental particle physics since 1980 and has participated in the discovery of the top quark and the Higgs boson. He is the author of The Lost Art of Finding Our Way and is currently a member of the Atlas collaboration at the European Center for Nuclear Research. In A Sense of Space, John Edward Huth uses navigation to help readers chart a path through evolving spatial models. Through this, he offers an astonishing exploration of how changing scientific models of space alter our social perceptions and vice versa, with accessible introductions to topics including mental maps, astrology, astronomy, particle physics, and Einstein's relativity. Huth shows readers how our understanding of terrestrial distance is routinely extended to realms far removed from our everyday experiences. Jacob Barandes completed his PhD in high energy theory in the Department of Physics at Harvard University, where he currently serves as a senior preceptor. He is also an associated faculty member with the Department of Philosophy and a faculty affiliate with the Harvard Black Hole Initiative. We are so pleased to host this event with the Harvard Science Center tonight. Please join us in welcoming John Edward Huth and Jacob Barandes.
Okay, thank you. Thank you, Jude. Okay, well, she already gave away the topic of the book, but let me just recap that. The idea is that there are social influences on how people think about space, and I'll explain how that seems to come about. And then when there are new visions of space that emerge, there are also kind of new visions, new social and cultural visions that emerge from that. And so I'll try to explain that. So let me just start off with one story that illustrates that, and I'll jump into the way the brain works to process both social and spatial maps, in effect. So in the ancients in Greece and Rome would write about a plurality of worlds. What is that? That's the idea that there may be some other worlds that harbor intelligent people like us or intelligent beings like us. And that's been around for a while. But here is one kind of remarkable first instance of the topic of the book is with the invention of the telescope, people could start seeing structure on the planets. So you could see the rings of Saturn, the moons of Jupiter, ice caps on Mars, and so on. And that immediately led to speculations that maybe those planets were inhabited. So the appearance of structure enabled by telescopes made people think that they were inhabited. And Christian Huygens, an astronomer from the Netherlands, wrote a treatise on exactly this point, that there was beings that inhabited Jupiter, the moon even, and Saturn, for example. And this persisted kind of in a cluster of astronomers and didn't really make it to the big time until the latter half of the 19th century, where there was this kind of rising interest in extraterrestrial life. And there was, in fact, a prize, the Guzman Prize, that was offered for somebody who could successfully have bidirectional communications with intelligent beings in the planets. And what was interesting was this prize excluded Mars from being included because everybody already believed that Mars was inhabited by intelligent beings. So this gentleman here is Percival Lowell, and He was from the famous Lowell family, like the house that we have here in Harvard, and took some of his wealth and went out to Flagstaff, Arizona, and built an observatory that was in a low light pollution area that was high and dry. And he started looking at Mars. So every 2 years, we're in close opposition to Mars. We come to have our point of closest approach. And there, people would train their telescopes on Mars and make drawings like this. And Lowell believed that he saw canals on Mars, and in fact believed that the canals on Mars came from an intelligent civilization that was channeling water from the ice caps down to the dry regions in the center of the planet. Now, this partly inspired H.G. Wells to write War of the Worlds, who knew of this work. And H.G. Wells also learned of an observation of a flash of light on Mars from astronomers that were reporting to Nature magazine. And the editors of Nature went on to speculate that these flashes of light was an attempt to communicate with Earth from this intelligent civilization on Mars. H.G. Wells was already kind of thinking about how the tables might be turned on Great Britain if they were invaded by a colonizing alien species of some kind. And so was off to the races. He wrote War of the Worlds. And at that point, the whole cultural phenomenon of extraterrestrial intelligence sort of exploded on the scene. And so we have that to this day with Star Wars and whatnot. This is an interesting headline here. It was in 1911 in the New York Times. And he made a drawing of the canals on Mars at one point, and then 2 years later, he made another drawing when we were in opposition. And because the drawings looked different, what was his conclusion? His conclusion was that the intelligent Martian civilization could re-engineer in only 2 years the canals of Mars. And then there was this kind of credulous headline, New York Times, like, kind of, God love them, they haven't changed since. This credulous headline, Martians build 2 immense canals in 2 years. So things haven't changed much. Okay, so where does this come from? Where does this correlation, where does this projection of human categories, human things into space come from? Well, we have some clues from psychology. This is a book by George Lakoff and Mark Johnson called Metaphors We Live By. And there's a chapter where they explore the language of the correlation between social and spatial terminology, if you like. So here are some examples. I'm on top of the situation. They've gotten close, so proximity is a stand-in for intimacy. Why are you so distant? They're high-minded idiots. I'm not sure where you're going with this. What are you trying to pull? So all of these are just examples of that, and I could just go on and on. I have pages of this sort of thing. And what's interesting is when I did this in a freshman seminar, we started talking, and we found that it was almost impossible to go any distance in the seminar without invoking a spatial metaphor of some kind. And so we would haltingly stop, kind of chuckle, get going again, and then we'd stop, and so on, until the point where it kind of wore thin. But it just gives you an example how impossible it is to dissociate the spatial and social in our thinking. So where does this come from? Well, we have a part of our brain, the limbic part of the brain, which is kind of the most ancient in some sense. There is a mental map that is stored there, and this is like the map that we might have as we're just walking around Harvard, for example, or our hometown or something like that. And you can have multiple maps that you store in there. And then they can get processed in some way that then goes out to this region, the parietal cortex, which helps you navigate in a specific pathway that you take. And cognitive psychologists say that there are kind of 2 senses of space that people have associated with the way they think. So one is called egocentric, where the space is referenced to the individual. So you think about where, I don't know, your bedstand is in your dark room when you're getting up and you're trying to put your hand over and grab, I grab my glasses, for example. And so you might designate space by front, back, left, and right. And so that's one way it can be done. And another is called allocentric, where it's more global or universal in some sense. And so there you might orient yourself with respect to north, south, east, and west. And people can swap in both. Sometimes languages tend to favor egocentric orientations, and some languages favor allocentric orientations. Some people say that the languages that favor allocentric orientations, the people are better at navigating, but we'll see. It's been tested by psychologists and anthropologists, and there's still some debate about that. So I take this to some extent as a jumping off point. And when I looked at models of space in Western physics and astronomy, what was surprising to me was that the need to populate it with humans or intelligent beings kept coming up over and over again, which seems surprising because I would have thought physics would be independent of humans in some sense. So what I tried to do was to broaden these definitions in some way. So an egocentric space would be, for example, a space that necessarily involves humans on Earth. So what would that be? That would be perhaps Aristotle's universe, where the Earth is at the center of his universe. An allocentric universe might be Copernicus's, where the sun is at the center of the universe and humans don't play a specific role there. So that's just one example of this binary, which surprisingly works. And it's not perfect, but it actually, to my amazement, we keep happening over and over again, is seeing the egocentric rear its head. So here's one speculation on the relationship between physical space and social spaces. So here's our physical space here, where you're just sort of wandering around, and I think about, oh, the restroom's over there, and the cafe is up there, and so forth. But then there's some intermediate domain where you associate social characteristics to that physical space. So you might think about the person who works down the hallway, or that house belongs to my neighbor, and so on. And so there's kind of an overlay between the social and spatial spaces in some sense. And then in more abstraction, there could be a two-dimensional space of affiliation where people are close together or distant from each other. And then there is a power dimension. So you say, you're getting in at the bottom, or I have to talk to my superiors, people at the top. And that this map seems to exist both in the hippocampus alongside of the spatial map. And this might explain why we have this connection between social and spatial cognition. Okay, so quickly through some of the spaces. Here is the space of Aristotle, where there is the Earth at the center, where half of the Earth has basically continents of Europe, Asia, and Africa, and the other half is made out of water, and then it's surrounded by air and then fire. And then we have these spheres that Aristotle posited, where there is a prime mover. When the Catholic Church took over this model, the prime mover presumably is God in some sense. And then you have the fixed stars, known as the firmament, and then these various spheres of Saturn, Jupiter, Mars, and so on, until you get to the moon. Now, here is a word of the day, which is kind of interesting. It seems like this model puts primacy on humans, but actually there was some sense in which us sinners who are imperfect live on Earth here, and there's a more perfect heaven outside of that. And so there's this word sublunary, and what that means, if you look it up in the dictionary, is of kind of this imperfect Earth. We're sinners, and there's a sense that there could be perfection, but we are falling short of that perfection. And what that comes from is, in Aristotle's model, the idea that the Earth is inside the sphere of the moon. So that's where that comes from. Okay, I talk about Dante Alighieri because here is an example where we have a space, Aristotle's space, and Alighieri populates that space with various individuals and various moral traits and so on. So we have the circles of hell for various sins that exist. And then we have these spheres we see from Aristotle that have various number of virtues associated with it. And then, although the concept of purgatory existed for the Catholic Church in Dante's era, Dante was the first person to actually give it a physical instantiation. And he called it basically a mountain with a set of terraces on it with different sins, and people would then try to ascend through Mount Purgatory. And It's at an antipodal point, that is to say exactly the opposite side of the Earth from Jerusalem. So here's an example of a space of Aristotle and then a population of that space in culture from Allegheny. I was interviewed by somebody from the Harvard Gazette who was doing a story about astrology, and they saw the little advertisement for my book, and they were saying, you're a physicist. Why the hell are you going to write and talk about astrology? And so I had to talk for a while about this with the reporter. And there is a physical space for astrology, and it definitely has some sort of social connection associated with it, because it can, supposedly we can predict people's characteristics. So my wife's in the audience, and she's a Leo, and I could explain what that is later if you're curious. And then I'm a Pisces, and I'm over here. And this is the ecliptic. And the ecliptic is basically a path through the sky that the sun, planets, and moon follow. And in astrology, it's subdivided into 12 different zodiacal signs. So here we have Aries, Taurus, and so forth. And because all the planets and the sun and moon are in kind of one plane, this makes the motion rather straightforward along this ecliptic. So if you want to know about today, right now, the sun is just about to pass from Scorpio into Sagittarius. So where the sun is approximately here, and unfortunately, getting lower in the sky until we reach the winter solstice, and we have these turning points: the vernal equinox, and the summer solstice, and then the autumnal equinox. So you might say, well, what good is that? People had practiced this form of astrology since Ptolemy in about 200 AD, and it persisted in the Middle Ages. And then there came a point where it actually turned out to have some utility. So there are calculations that you can do to figure out where planets are in the sky and how they map into these zodiacal signs. But also, if you know where you're born and where the stars are in the sky, you can figure out your natal star chart. Here is a almanac, and if somebody wants, in the question and answer period, I can take out my decoder ring and explain it to you, but it looks like hieroglyphics here. This was written for the period of 1475 to 1506, and mainly intended for astrologers. But what happened in Portugal was that the Portuguese wanted to go around Africa to get a route to the Spice Islands. And what they did was they took astrologers and put them on shipboard, and then had them basically reverse engineer astrology in such a way to become celestial navigation. And in fact, Columbus, who lived in Lisbon for quite some time, picked up on this, and he carried this almanac with him in his 4 voyages to the New World, and practiced celestial navigation using the tools of astrology, which I found rather interesting. So there's a case where kind of a social model influenced a technological breakthrough of some kind, and so you can just, again, see this interplay going on. Okay, well, fast forward to Newton, and Newton came up with a space that had, at least by his phraseology, an absolute space and absolute time in the sense that the clocks always ticked the same everywhere throughout this space, and the space didn't need people in some sense. And this perturbed some artists. So for example, William Blake really detested Newton because all of a sudden he removed people from the equation and God from space and that sort of thing. So okay, that was interesting point there. And then as we turn to the latter half of the 19th century, people were trying to understand electromagnetism, light, how light propagates, and there was a belief that light propagated through some medium in space called ether, and attempts to measure our motion relative to this ether failed, and it looked like perhaps the speed of light was a constant for all observers. There were some patches done by various physicists that seemed to work, but for Einstein, these patches seemed to fall short. And he was kind of obsessed with solving this riddle of how to do, there was something deeper there associated with it. And he had an argument with one of his friends, Michele Besso, and the next morning he said he figured it out. And so how did he figure it out? What did he figure? So he was under the influence of another earlier physicist named Ernst Mach. And for Mach, there was no kind of theory that held things together like Newton's theory, but that physics was only relationships between observers and things that you observed. And so what struck Einstein was if he started to talk about observers who had clocks in front of them, that the way he defined time would be defined by the hands of the clock as opposed to some absolute time that's moving along. And then later on, he developed this idea of curvature of space-time to describe gravity. But there was an example, at least the inspiration for Einstein was sort of thinking about people inhabiting spaces. I wouldn't say that special relativity really needs that. It doesn't, but that was kind of the inspiration he got. Okay, so quantum mechanics, you would think physics would kind of be devoid of people and we would just talk in generalities. But quantum mechanics describes matter as a wave. And so you have waves like a photon, a carrier of electromagnetic light, let's say, and it's spread out in space and has a variety of energies associated with it. But then something odd happens. So here you have a camera set of sensors and a spread out photon in space. And then when the sensor is activated, that spread out photon all of a sudden appears at one tiny spot and with one very specific energy. And so this kind of is like the photon disappears and just kind of its remnants are basically in one spot in the camera. And so this has puzzled people for quite some time, and Jacob still is kind of fascinated by this topic. So we've never really solved the quandary. But there are ways of calculating this process. But the one thing that was interesting was the early practitioners of quantum mechanics believed that consciousness was necessary to do this, collapsing this wave packet. And there are a number of them that believe that. And although I think most physicists these days don't really subscribe to that consciousness idea, it's persisted in a lot of New Age books about quantum mechanics. And you see this consciousness related to I don't know, thinking about changing water molecules in a bottle or something like that. Okay, so this is kind of the last concept I'll throw at you, and then we'll get to the discussion. One of the ambitions of physics is to describe nature at all scales and to come up with a unified field theory that describes everything. And we've done rather well up till now. And so here is a range of distance scales in meters that kind of spans what we've been able to probe experimentally. So I'm at this experiment in Geneva, Switzerland, and we're getting down to 10 to the minus 20 meters in our probes. And then if you ask what the edge of the universe is from what we know now, it's about 10 to the 26 meters. Curiously enough, halfway in this weird scale that I've constructed, halfway between these two is about 1 kilometer. And so this halfway space between the two is kind of like walking around the neighborhood. And I always found that to be an interesting coincidence. So the processes of stars by which they burn lighter elements into heavier elements seem to be exquisitely tuned. And so if you just mess with some of the parameters a little bit, it seems like life on Earth would not be possible. Furthermore, to achieve this ambition of unification, we have to go way out to about 10 to the minus 35 meters when quantum mechanics and gravity, we believe, mesh together. And this remains a project within fundamental physics to describe this properly. And there's a problem that arises. If you try to take the unification of the forces at that scale and run it down to the scale that we're probing out in Geneva, Switzerland, you get something called the fine-tuning problem. And this fine-tuning problem persists all the way to perhaps the edges of the universe in some sense. And it seems miraculously that we're actually here. And so just to illustrate this, here are two versions of pi that only differ in the last 30 decimal places, last point in 30 decimal places. So that gives you some sense for this. So this seems very unnatural. And furthermore, in at least string theory, which is an attempt to try to be an overarching theory of everything, there can be 10 to the 500 possible universes, and yet we're in this one particular one. So now you could imagine, well, you shrug your shoulders, but there's an idea that has taken hold among some theorists, and that is called the anthropic principle. So here we have people coming back in to these models of the universe. So the idea is roughly this, that we happen to inhabit this universe because it allows us to inhabit the universe. And in fact, there's even a stronger version of this, which is that in order to exist, universes have to make conditions habitable for life. So I won't comment on that particular the point. But here on this vertical axis, you have the number of possible universes, which may be gigantic, and then time with the universes sort of evolving in a sense. And then there happens to be this kind of sweet Goldilocks zone that is amenable to human life. So here you have the existence of humans as a way of trying to explain the universe we live in. So again and again and again, we just have humans sort of coming back in, back in, and back in. So that's an interesting observation. So there's a lot more to the book, but obviously I can't go on forever. Well, you have questions, obviously, you can ask them where we're going on. A few shout outs. So I already pointed my wife and my daughter. Let's see, my editor, Joe Calamia, who is instrumental and was hounding me until I actually got this done and did a lot of work. And a special shout out to Cheryl Blanchard, who she took my online course on meteorology, and then we had some back and forth, and then she agreed to be a reader for my proto chapters. And she's right there. Just raise your hand, please. And her husband Lance. And she just did an amazing job keeping me on target. I remember, I'll just give one particular instance, which was I had to rewrite my chapter on cosmology for various reasons, like my editor wanted me to do it. And so I cranked out a version, trying to just get it out of the way, and she read it and said, this is kind of flat. And so, I said, okay, well, let's roll up our sleeves and, sit down and really try to do it justice. And I think it turned out much better, and it's because kind of, get some honesty, about, does this read well or not? And so Cheryl, has just been amazingly helpful in the production of this book. Okay, so that's the talk, and here's Jacob. Oh, Jacob also would visit my office a lot, and I'd throw out things, and he would shoot them down periodically, or tell me stories. So we had fun. He helped me too.
Yeah, when you visit John's office, you always learn something new. At least one thing, if not many. All right, so I have a bunch of questions for you.
Okay.
You've written a book called A Sense of Space.
Yes.
You've talked a lot about different ways that humans understand space. What is space?
I just went through about 10 examples.
Well, sure, those are examples, but like...
Okay, you have to ask, what do you think is space?
What do you think space is, as someone who's written a book on it?
Yeah, I think, I look at it as kind of a stage in which you can populate, a play, if you like. So, there's a play you want to put on, I don't know, Merchant of Venice or something of that nature. And so then you roll out, the props and the actors and that sort of thing, and then they populate that. So I view space as kind of a stage on which, the theater of the universe acts out.
Yeah, so there is physical space. There's the space that we live in, right?
Yes.
Heisenberg once said, the sky is blue and birds fly through it. That's what he means by space.
Oh, very good. I didn't know that.
But physics has introduced a lot of other kinds of things that are called spaces of different kinds.
Yeah, sure.
Yeah. So there's the physical space we live in, three-dimensional space that we think we live in. This has been extended. It was extended by Minkowski to four-dimensional space-time. Time is included. Today there are theoretical physicists who talk about extra dimensions.
Yes.
And these extra dimensions are supposed to be kind of like physical space. They're extensions of physical space. If you were very, very, very tiny, maybe you could move through them. In some conjectural models, strings can move through them. But there are other kinds of spaces altogether. There are various kinds of parameter spaces. When physicists build models, they imagine like the models populating an abstract space where every point represents a different kind of model with different values of various parameters. And one of the things that physicists try to do is figure out which regions of parameter space are still viable, which ones have been ruled out. There are configuration spaces. There are phase spaces. There are Hilbert spaces.
I was going to mention that. You beat me to that. So for everybody who doesn't know what a Hilbert space is, when you talk about quantum mechanics, there are ways of describing the calculations in quantum mechanics for the way these particles kind of interact and move about. And this thing that he's calling a Hilbert space is this technical description that we use for that.
So my question for you is, why do we call all these things spaces? We can't walk through them or move through them. What is it about the notion of space that we find so intuitively helpful and graspable that we keep talking about these abstractions, which are not places where birds can fly?
Yep.
Why do we call them spaces?
I think it describes possibilities. I mean, it gets back to the idea of a stage in a theater where, you know, the possibilities can get addressed, and then there are physical realizations of what we're actually experiencing. So if we talk about your quantum mechanical Hilbert space, you know, you could
Not
talk.
mine.
Well, our. So you could talk about a hydrogen atom. So a hydrogen atom's in one state where an electron is more excited, and then there's one where the electron is less excited. So you have this possibility, these possibilities of electron states, but then, you know, there's this physical transition that you can calculate, and so you again have the possibilities, but then the possibilities has, you know, an instantiation associated with it. So I think that's my answer. Possibilities where things can play out.
Yeah, because of course in mathematics people talk about sets. We talk about sets of possibilities, right?
Yeah.
When you're considering things that you want to do, you've got a company, you've got an organization, you've got a group of people, and you want to make some plan, you talk about a set of possibilities. The idea that we want to talk about these sets of possibilities as spaces of possibilities is very interesting.
Yeah. Well, just the ubiquitousness of the way our brain works,
Right.
I think, is probably
Right.
the explanation.
Yeah, those wave functions, right, that we're talking about, back in the very early days of quantum mechanics, Louis de Broglie proposed that particles had these waves associated with them that lived in physical 3D space. Today, physicists actually put wave functions in either, depends on how you think about them, in configuration space, which is a set of possible arrangements, or in Hilbert space, which is far more abstract.
Yeah.
And you know, it gives you a sense, right? Physicists do put things in these spaces, even though they're not maybe places that we can move through.
Yeah. Well, the possibilities.
Possibilities.
I mean possibilities, and that's sort of why the social construct works. Or moving through time is like moving through space. You know, we put the past behind us and walk into the future ahead of us and that sort of thing. And so again, these are possibilities of what, you know, might occur.
Yeah. When we think about space, especially when we think about space in, as you put it, egocentric terms, at least when we're talking about physics, we think in terms of reference frames.
Yep.
I was hoping you could talk a little bit about what role reference frames play when we think about space. Many people probably heard of reference frames. Why are they so important? What role do they play in helping us make sense of where we are?
Well, the simplest ones are the ones of Newton and Galileo, where you could imagine, you know, a train and a platform, and the train's moving at some speed, and the platform, like there's somebody sitting on the platform. And the laws of nature basically would say that there is no distinction between the train moving and the platform. And then the laws of physics basically kind of play out the same way. And so there are things that we call invariants. So imagine somebody dropping a ball, and the ball accelerates downward at a certain acceleration. Somebody on the train measuring that ball dropping and somebody on the platform measuring that ball dropping would see the same thing. And so the idea is that laws of physics are independent of those two frames of reference. Then when we got to Einstein, and Einstein's, at least his special relativity, he imagined two frames that are moving by each other. And rather than having this absolute time that Newton talked about, what had to happen was, to get the speed of light to be the same for all observers, he had to mix up time with space, and so time became a function of space. And so this idea of two frames of reference and the rules between how you get from one frame of reference to the other, or do measurements in those two frames of reference, got modified by Einstein. So that's just one sort of example of an evolution of frames of reference.
Speaking of Einstein, in the book you talk about Einstein's complicated relationship with Ernst Mach. Sometimes it was a relationship that was one of admiration, at least from Einstein's part.
Yes.
Einstein ended up delivering a very famous eulogy to Ernst Mach in 1916 when Mach died. This was right at the beginning of, you know, Einstein's rise to fame. He, you know, introduced his theory of general relativity, the final form of it, in 1915. And then 1916, Mach died, and then a few years later was the eclipse experiment that made Einstein interact. Now you just draw a circle, at like a diagonal line on top and a diagonal line in the middle, and everyone's like, Einstein, right? That's when he went from a nobody, at least in the wider public, to Einstein, the icon.
Yeah.
So it was a very important moment, but their relationship was complicated.
Yes.
And Mach himself had some strong views about how to think about science, how to think about where we were in space, views that were also in opposition to views of people like Max Planck, who's responsible for some of the early development of quantum mechanics. Your book talks a lot about history.
Yes.
And this history is really interesting and very relevant to how we think about these questions.
Yes.
I was hoping you could talk a little bit about what was Max Planck saying, what was Mach saying, why did Einstein admire what Mach was saying, what happened to the relationship between Einstein and Mach?
Yeah.
Yeah.
Well, let's see. So one of Mach's influences, besides thinking about observers and that kind of the laws of physics were only really reports between observers, and there was this famous thought experiment that Mach had too, which is that if you stare at the stars in the sky and then you spin around and your arms go up as you spin around, that sort of defines a kind of specific kind of reference frame for the universe. And so those two things will help get Einstein thinking about gravity, thinking about kind of bootstrapping into special relativity, for example. I think Mach also evolved over time because as he sort of got towards the end of his life, he started doing investigations and perceptions and that sort of stuff. So he really kind of went down the rabbit hole of his idea that only relationships between observers count. Planck was also a very early supporter of Einstein as well and encouraged him a lot. Planck was, I guess, for the first person to really intuit quantum mechanics in some sense by doing fits to kind of a thermodynamic thing called black body radiation. You don't need to know that. I'm just sort of telling you what he did. And kind of toward the end there, Planck became very critical of Mach to the point where he said, the laws of nature, the laws of physics should be independent of human presence. And that kind of is back to this strong allocentric perspective that I talked about in the beginning, whereas Mach was going into kind of a strong egocentric view of the universe. And at the very end, I believe there was a book that Mach published, and I forget the exact subject matter, but I think it had to do with perceptions. And in his preface, he disavowed Einstein altogether, which must have been crushing to Einstein because he admired Mach greatly.
Yeah, debates over the nature of space by philosophers. Mach was in part a philosopher. And going back farther to what you'd call the natural philosophers, the precursors to people we would now call physicists, there was a debate raging about the nature of space. Newton thought of space in terms of what I guess one would call it absolute space, that
yes.
There was this stage. Newton's own theory suggested that we could never detect which frame of motion was the rest frame, the frame of absolute space, but he still felt like he needed it as a crutch in order to explain
yes.
what motion was, yes. Without there being some underlying grounding notion of absolute space. It was not well defined to talk about things moving. Leibniz, famously a philosophical, intellectual competitor of Newton, suggested that one should instead think of space relationally.
Yep.
That what it meant to say that things had locations was only that they were in locations relative to other things. And that motion should be thought of in a relative way. This was a very, and you could think of this as a very advanced, precocious view about things that would later happen. Mm-hmm. How should we think about that debate between relationalism and absolute space if we're coming at space from thinking about egocentric versus allocentric?
Yeah, I don't think it's entirely solvable because, our brains kind of work in both modalities. So, if you go strongly in one direction, people are going to kind of push in the other direction. And it's almost like...
You notice the language he's using?
Yeah, exactly. Direction. Yeah, no, that's kind of the point of the book is that we have this tension between these two modalities of thought, and in a sense, we can never really break out of it. I mean, that's you can have this one strong allocentric view, and the laws of physics should not be absolute in some sense, or they can be relational in some sense, and it just keeps playing out over and over and over again. You should see, I've written a fair amount about this debate between the people that advocate this anthropic principle and then ones that think that physics should not have to deal with humans whatsoever, and it's still going on. I mean, that's another example of that discussion.
There's an obligatory question I have to ask when I ask about the Leibniz-Newton debate about absolute space versus relative space. Okay. So philosophers of science, people who work in philosophy, are interested in questions about the metaphysics of space-time. There's an ongoing debate. I'm going to ask you this question. Maybe you all think about it. If you took all the objects in the universe, every single object in the universe, everything, planets, people, galaxies, all the dust, everything, and you moved everything 10 meters to the left, or if you're an American, 30 feet to the left, like everything, did you actually do something? Is anything actually different now? Leibniz would say no, because all that really makes a difference physically is the relations between things. Newton would say yes, but you might not be able to tell. I mean, obviously, if everything moved 10 meters to the left, there are no instruments that would tell us where we are. But there's a dispute between the two of them, and a dispute that goes on right now.
Yep.
What do you think?
Well, I think it doesn't matter. in a word. Let me throw another one at you, though. This is something that when I was a kid, my God, when I was in 5th grade, would you believe I read a book on special relativity?
I believe it.
Yeah. So,
I think they can all believe it.
When I was a boy, my father, when I was 8 years old, he'd read me bedtime stories. He bought me a book called The Wonders of Physics, reading The Wonders of Physics to an 8-year-old boy. Okay. So in this one book, they said, okay, what if everything in the universe expanded by a certain amount? That is, the atoms, the protons, the galaxies. Would it make a difference? So rather than just moving everything over 10 feet, what happens if it expands a certain amount? And we had a theorist here named Sidney Coleman who was just amazing. And I was afraid of asking stupid questions, but this question bothered me. So I actually grabbed Sidney and kind of pulled him aside and said, what happens if everything expanded by a certain amount? Would it make a difference? And he actually had thought about it, and he came back with kind of an interesting answer. So.
Did he say Brooklyn is not expanding?
Yeah, right. So anyway, that's a variation on that. If everything expanded by the same amount, would the universe be different? So.
I want to be mindful of the time, so I'm going to ask you one more question, and then we'll go to Q&A. Okay. You talk in this book about the overview effect.
Yes. Oh, yeah, right.
You talk in this book about the psychological experience of astronauts.
Yes.
You talk about solitude. You talk about the overview effect.
Yep.
There's a very famous soliloquy, monologue, short essay by Carl Sagan, who also comes up in this book. So the story is that we sent a space probe, not we, I wasn't part of it, we, the collective humanity. Humanity sent a space probe way, way, way out into deep space, and Carl Sagan— Pioneer, right. And Carl Sagan argued that they should take one picture of Earth from the far reaches of the solar system. And there was some debate over whether they should do this, is it really scientifically useful, and he said, you should really do this, and they turned it around and took a picture of Earth, and it led to this very famous picture that came to be known as the pale blue dot. Carl Sagan wrote a book called The Pale Blue Dot. And it's just an image of Earth as a pixel, a tiny pale pixel. And remarkably, the way the picture was taken, there's this sunbeam, and Earth is just suspended, this tiny, fragile little pale blue dot suspended in a sunbeam. And he wrote this long discussion about it, which I also take to be a version of the overview effect.
Okay, yeah.
What is going on with all these people when they go out into space? What happens to them psychologically? Why do they have these experiences? What is the overview? What was Carl Sagan talking about?
So let me explain the overview effect for some of you. It was coined by a writer named Frank Drake. And his belief was that if you go into outer space, you'll be transformed by looking back at the Earth and sort of seeing the Earth as kind of being this kind of unified, the ecology systems of the Earth would be unified, our role in the Earth would be unified, and all of this thing is kind of this inseparable whole. And so that kind of is a sense of the overview effect. It's not universal, by the way. Some of the early test pilots that would venture up very high in altitude had something called the break-off phenomenon, where they would experience tremendous amount of anxiety at being kind of divorced from the Earth. So it was kind of interesting. There were psychological studies where the test pilots would go one way or the other. Some of them would experience this epiphany and be ecstatic about it, which I guess would be the overview effect, but some of them experience a lot of anxiety at being separated from the Earth. And one curious thing, I'll just sort of give a preview of that particular chapter, was that there was a lot of psychological work testing the Mercury astronauts. But then at a certain point, they put a quash on all psychological data coming out of the Mercury program, which leads me to wonder whether or not there was kind of a false report of heroism that was happening, and some of them were experiencing this anxiety from this so-called break-off phenomenon. So that's my 2 cents.
Thank you, John.
Okay.
Let's turn it to questions.
Yeah.
Thank you so much for the wonderful talk and for the conversation. Can you elaborate a little more about the interpretation of quantum physicists on the role of consciousness, on how to interpret the phenomena, the journey of assuming consciousness is needed to describe the collapse of wave function to now that you said they're not taking that?
That first arose from I think the grandson of Charles Darwin, who was a physicist at Oxford, and there was a conference in Copenhagen, I think in 1929, where that assertion of consciousness first emerged, and there were other physicists that articulated it. And kind of the idea was that even when light enters your eye and the retina, you still have this wave function sort of spread out in space. And then it gets processed, and then there's some sort of a cut, as they called it, where it got transformed into a wave function into an awareness. And it was like that transformation from kind of into the awareness that was what was causing the wave packet to collapse. So that was their idea, basically. So that's where that came from. Well, I should ask this guy, but
this is what keeps me in business.
Yeah,
wherever we are, questions about quantum mechanics come up.
This is actually a huge discussion on the peripheries of physics, this philosophical point. And so you've raised a question which, at some level, I can't answer other than to say we don't have really a model of consciousness. I mean, this is the thing where I found it a bit odd that people are telling that consciousness collapses the wave packet because there was no model of consciousness. I mean, you read somebody who writes a treatise on quantum mechanics back in the day, and there's this math, and then they get to this, and it's just words. So there's no theory of consciousness in there, no mathematical theory formulation of consciousness, and then there's just these kind of assertions that are made, and it's like, well, okay, how can I get it? I mean, there are time scales. The time scale of the collapse of the wave packet is kind of incommensurate with the time scale for how we think. So that maybe is suggestive that it's not a real thing.
If I may just add a quick couple of notes about some additional history. John von Neumann, the great mathematician, heir in some sense to the greatest mathematician of all, after David Hilbert, of whom Hilbert spaces are named, wrote a treatise on quantum mechanics published in 1932 in German. And there's a section toward the end where he talks about the measurement process. This book was not translated in English until the 50s. The first English edition, I believe, came out in 1955. And people didn't quite understand what he was trying to say. Eventually, the idea that consciousness was really central to the collapse of the wave function is associated with Eugene Wigner, a theoretical physicist who wrote an article about it called Remarks on the Mind-Body Question in 1961. And this view has now been associated very strongly with Wigner. I would say that there are very few physicists nowadays, and almost no philosophers, who think that human consciousness, or consciousness broadly defined, is responsible for the collapse of the wave function. There are some exceptions. So some of you may know David Chalmers, who is a philosopher of mind who's worked on consciousness, and he's played around with some versions of quantum theory in which consciousness plays a significant role. But I would say it is not a widespread view. Most physicists and most philosophers either think that collapse doesn't truly happen and that it's really an artifact of some kind of approximation or not an incomplete version of quantum theory, or the ones who do think it really happens, they will attach it to some other physical mechanism, something that kicks in when enough degrees of freedom when enough variables get into the problem, although it's still an open area of work. Again, this keeps me in business.
I was reading the abstract quickly. Is multiverse a reality or human imagination? I think it taps into the anthropic principles that you meant.
What was the first thing?
Is multiverse.
Mount Everest?
Multiple universes, multiverse, in the app.
Multiverse.
Oh, the multiverse.
Yeah. Is a reality or human imagination? I think it taps into the anthropic principles you just mentioned. Imagine if human never ever existed, would there still be such concept in multiverse?
Well, the multiverse is, in a sense, an attempt to try to explain, why we're in this improbable situation. And so it really kind of comes from the imagination. If there are variations on the multiverse, there are a number of variations on the multiverse. So one is that when there's a wave packet collapse, that the universe forks into the different possibilities associated with it. And that's become, speaking of cultural manifestations, is this idea has become part and parcel of movies and TV shows and things like that. So that's one version of the multiverse, which is this kind of splitting off when a wave packet collapses. And there are other ones, which is like this one, with different parameters that kind of exist. And then there's a possibility that there are many universes, like where did we come from? And Brian Greene, for example, sort of explained it in a Swiss cheese model. So you have a block of Swiss cheese, and then you have the little holes are the universes, and even though they're expanding, the block of cheese is expanding faster than the little holes of Swiss cheese in there. So those are just two. And I think Brian wrote a book where he kind of categorized all the different kinds of multiverses. But it's fair. Yeah, oh, well, Susskind, yeah, I have a long quote about Susskind in my book where he tries to basically push the, not only the multiverse idea, but the anthropic principle, and tries to get real serious and chides us physicists for being too ambitious for trying to describe everything from scratch. Yeah, we haven't measured it. I mean, in fact, that's another question, is if you can't test it, is it real? And that was Paul Steinhardt, who's an astrophysicist, sort of came back and said, well, if you can't test it, what does it matter? Does it have any reality if you can't test it? Which is why in that scale, I only put the distance scales that we've empirically been able to probe and leave the rest up to kind of question marks.
I think it's amazing we've reached a point in the culture in which you'll see a movie or TV show and something weird will happen and someone will say, well, why did this happen? And someone will say, the multiverse. And everyone's like, okay. There was a time when the multiverse was such a staggering concept that it would be, it would require all this explanation, and now it's just like, oh, why'd that happen? Multiverse, got it, good.
Yeah. Well, the multiverse also sort of became a metaphor for decision-making processes as well. And so you kind of wonder if you make a decision about, getting up in the morning and going somewhere, then, there's the other self that doesn't go anywhere and stays at home or something like that. And so, the things that you didn't do when you made a decision, there's another universe out there where, those things that you didn't do, you do, or something like that. And so multiple universes exist. So I view it as a very powerful metaphor, which is why it probably took off in culture.
Thank you for a very inspiring talk. At one point, when you were describing the different models for how you evaluate the theories about the universe, you were talking about degrees of abstraction, and that some models were much more abstract. And I was just wondering how you quantify that amount of abstraction. Once you get beyond something that you can't directly experience physically, everything seems to be abstract. And so is there a scale by which you quantify abstraction?
I'm not aware of one. I mean, it seems like it's more of a kind of a subjective, hold up your thumb. Is this more abstract or less abstract? Certainly there's no formal sense of abstraction that I'm aware of, although there may be some enterprising, mathematician or cognitive scientist who has a theory of abstraction out there, but I'm not aware of it. The one thing that I guess I would say is that, our sense of space has started out with something, relatively localized. So the pre-Socratic philosophers believed in a flat Earth. Then there was slowly motion to, a spherical Earth, and then the Earth was the center of the universe, and then the sun became the center of the universe, and so on. And so the way I would put it is that the domain of space keeps expanding in our imagination. It's not that, yes, the universe is expanding, but also our sense of what constitutes the totality of the universe that we inhabit. The distance scales keep increasing in some sense, but also decreasing in another sense when we're probing with successively higher energy particle accelerators, you're probing shorter and shorter distances. So both the domain to the large and the domain to the small is basically, changing so that we have more and more distance scales that we're probing. And in that sense, we require more abstraction. So if you look at the history of physics, particle physics, which is what I do, is that there's sort of more and more that comes into play as we go further along and we probe shorter distance scales and kind of wonder what's going on. So I don't know if that answers your question, but that's the way I look at it.
I have a finger on that.
Okay.
You're talking about abstraction, enormous scales, the course of history. I would feel remiss if I didn't bring up Archimedes' sand reckoner, which is maybe one of the most extraordinary scientific documents ever written. When I teach classes on physics, I try to mention, when I'm talking about the historical discussion of outer space, the sand reckoner, which is about space, but also about abstraction. I'm sorry, but could you just say a few words about this? Because it's just so incredible that this document exists.
Yeah, okay. So when Cheryl told me that my version of the cosmology chapter was flat, I was casting about for some way to introduce it. And so I went back to this thing called the sand reckoner. So this was something that was written by Archimedes.
And when is this we're talking about? Years?
200 BC, I think.
200, yes. Several hundred, I think it's 2,500 years ago, something like that.
Yeah, long time ago. Anyway, he wanted to calculate how many grains of sand would exist in the universe. And back then...
Could exist. How many you could fill the universe with. You could fill it out with,
Yeah, and so that model was, basically there was a model by an astronomer named Aristarchus who correctly was on the trail of trying to place the sun at the center of the universe at that time, and had distance scales that represented kind of the size of the Earth-Moon distance, and the Earth-Sun distance. And that was probably kind of what most people thought of at that time as the universe. But then Archimedes expanded that and said, well, there's a sphere of fixed stars, and I can calculate how far away this sphere of fixed stars are, and can I calculate how many grains of sand could fit in that volume. And to do that, he basically had to invent the mathematics of very large numbers and how to handle that. So we use exponentials these days to 10 to the 20th and 10 to the minus 20th and so on. But he invented that with a myriad, which is 10,000 in Greek, and then a myriad of a myriad and so on. So he kind of created this whole mathematical schema to be able to deal with huge numbers and calculate it. I think in our language, 10 to the 63 grains of sand in the universe. So I had to do this and say, okay, well, we now have a bigger radius of the universe, and so I did the calculation. It's like 10 to the 93 grains of sand in our current universe. So that's kind of the remarkable story of the sand reckoner.
Thank you for the talk and the introduction. So is the space continuous or discrete? That's one way to look at it. And the way why I'm asking this is because we understand space as a continuous thing, but our math is kind of discrete, because when we translate this continuity to numbers, then we have infinity, which is like we can't get hold of it. So then all sort of infinities come to place that we cannot do anything with them. So how we can solve this dilemma that the space is continuous, but our math is kind of discrete, and we do the calculations?
Well, I mean, our math can be continuous. I mean, that was sort of the point of calculus and Newton, was to actually, go from, kind of discrete chunks to something where you could actually calculate the orbits of planets as a continuous function. There is one thing that sort of brought to mind was when people are dealing with quantum gravity, which is not a solved problem, but there are people that speak of a space-time foam. So you get these little tiny processes in the vacuum where it is discretized in some sense. But that's not been proven, or not even experimentally, amenable at this moment. So.
We're at the end, but I do want to conclude with one last question for you.
Okay.
You've learned a lot about space.
Yeah.
You've written an incredible book. Everyone should buy this book. It's excellent. You've acquired a lot of wisdom on this, among many topics. If you wanted to communicate something to this audience about what you've taken from this, how you think about the world and space, what larger lesson do you think you would want to share given all of your research into this topic? What do you want to communicate to everybody?
I guess at some level, it's difficult to step out of our brains to look beyond, and we sort of want to. So there's this ambition. Why did human beings sort of migrate out of Africa and sort of explore every corner of the world? I think it's intrinsic to us to kind of be travelers, and the way I look at it is life is both a metaphorical and a literal journey. So I think that kind of getting back in touch with your own wanderlust is something that I'd like people to take away from this.
Thank you.